Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module HR diagram, color magnitude diagram from the paper Astronomy and Astrophysics. So students, after studying this module, you will be able to understand that the stars of a cluster were born together and have the same broad chemical composition but may have vastly different masses. And you will be able to learn that the color magnitude diagrams of clusters show most stars on the main sequence, but a few having moved away from the main sequence toward their giant branch. You will be able to recognize that the turn-off point, the point at which the stars they move away from the main sequence, is an important data for clusters because this gives the information about the age of clusters. Lastly, you will be able to understand that lower the mass of the stars, for the redder the color, at turn-off, older is the cluster. Low mass stars stay much longer on the main sequence before evolving away towards the giant branch. Next, you will also appreciate that open clusters are younger, while the global clusters are much older, the oldest having the age only slightly shorter than the age of the universe. So let us start with the basic introduction about the module. In the last few modules, we have been discussing the HR diagrams and its importance for the astronomer. We found that all the characteristics of a star can be found once the position of the star is known on the HR diagram. So if for an example, a star is located on the giant branch, then we know its surface temperature, spectral class, mass, radius, and the kind of nuclear reactions that are going on in the core of the star. That is why when a new star is discovered, the attempt is to determine its location of the HR diagram. So since a star of a given spectral class could be a dwarf, it can be a giant or a supergiant, we had to find out some way to supplement the spectral classification with a classification which would allow us to describe more comprehensively the class of a star. This supplementary classification is called as the luminosity classification, which we have discussed already in the last module. So the luminosity classification classifies the stars as first the bright supergiants, second normal supergiants, third giants, fourth subgiants, fifth main sequence, sixth subdwarfs, and seventh as white dwarfs. So when we include luminosity classification, a star or spectral class G2 on the main sequence is designated as G25. So we also found out that it is easier to find accurately the color of a star than determining its surface temperature. So moreover, the color is found to follow faithfully the surface temperature of stars, as we have discussed in earlier modules. Therefore, astronomers find it easier to draw a color magnitude diagram rather than the usual HR diagrams. It turns out that such diagrams for stellar clusters lead to the determination of the ages of clusters. So since the stars of a cluster can be reasonably assumed to have been born together, the stars can differ only in their mass and to a small extent chemical composition. So the last two characteristics of the star of a cluster allows us to estimate the ages of clusters, which is the subject of discussion in this module. Color magnitude diagrams of stellar clusters. Now this figure shows the color magnitude or the CM diagrams of stellar clusters such as Pleiades, Praesepe, M44, M92 and M67. So in the case, since the color of a star, it is easier to determine than its spectral class, so astronomers prefer color magnitude CM diagrams. In the case of Pleiades cluster, all the stars appear to lie on the main sequence. In the case of Praesepe and other clusters, most of the stars again lie on the main sequence, but an important point to notice is that a few stars have turned to the right from the main sequence towards the giant branch. So the point at which the stars turns to the right from the main sequence is called as the turn-off point. Galactic cluster Praesepe M44. Now this shows the CM diagram of open cluster Praesepe M44, and here the turn-off is easily recognized and shown by the orange dot, and the turn-off is at B minus V, approximately 0.2. Notice that here y-axis has the apparent magnitude, and the stars which have evolved to the red giant stage have also been identified. So a star more massive than those at the turn-off has also been identified by the blue color. Such stars are called as blue stragglers. Now students, each star of the cluster has the same distance modulus. Therefore, the apparent magnitude has to be adjusted by a fixed amount to get the absolute magnitude. So this adjustment does not affect the shape of the diagram, and the stars in the pink strip are giants. Globular Cluster M92. So this figure shows the color magnitude diagram of Globular Cluster M92. So the squares are measured colors and brightness for individual stars in the cluster. Now here the turnoff is at B minus V, approximately 0.4, much larger than that for the Galactic cluster M44. Now the lines shows model predictions for the positions of stars for cluster ages of 12, 14 and 16 billion years. So curves overlying the CM diagram are isochrones predicted by the models of the clusters. Isochrones for 14 billion years seems to fit the CM diagram well, indicating the age of the cluster around 14 billion years. Now this shows the cluster M67 and NGC 188. These are two of the best studied open clusters. The age of M67 has been estimated to be between 3 to 5 billion years. The latest estimate is being 4 billion years, and if this estimate is correct, it implies that the stars of this cluster are younger than the Sun. The diagram over here also shows blue stragglers. Evolutionary track of one solar mass star. So this figure sketches how a star of a mass about one solar mass evolves in the plane of the CM diagram, while on the main sequence the stars burns hydrogen. Once a hydrogen in the core is exhausted, the star expands and heads towards the giant branch. Now, when the second stage of nuclear reactions, helium burning, begins, the star heads back towards the horizontal branch. So, once in its life, it will become a variable star. Pre-main sequence evolution of stars. So the general picture of a star formation is that the stars are formed from the interstellar material when a large gas cloud becomes gravitationally unstable and breaks up into small pieces. Each piece or a protostar contacts because of the mutual gravitational pull of particles and eventually become a star. As a protostar contracts to form a star, it appears to the left of the main sequence as pre-main sequence star. Its initial temperature is quite low. Nuclear reactions cannot ignite inside it. So as it leaks or it keeps contracting, it is keep on contracting again and again. Under gravitation, the density and pressure inside it increases. So a part of the energy is released by the gravitational contraction increases its surface temperature and the protostar starts moving to the right on the HR diagram as shown in this figure. So when conditions within the protostar are right for nuclear energy generation, the pressure inside it builds up and a stage comes when it is high enough to halt further contraction. So at this stage, we say that a star is born. At this time, the star is on the main sequence and its age is reckoned as 0. For this reason, the main sequence is also known as the zero age main sequence. So this figure shows the effect of mass on the evolutionary track. Of the main sequence, the evolution depends on the mass of a star. So stars of masses approximately greater than 5 molar mass, solar mass basically, have very complicated tracks, many aspects of which are not properly understood. The lifetime of a star on the main sequence or the main sequence lifetime. A star stays on the main sequence as long as it can burn its hydrogen to produce helium. So once the hydrogen content of the core is consumed, the star starts moving away from the main sequence, which has been previously discussed. So when the next stage of fusion reaction begins, nuclear reactions happen, which will be discussed later on, and the star turns back towards the main sequence. However, at some time in its life, the star will pass through the instability strip on the HR diagram when it becomes a variable star. The time for which a star stays on the main sequence depends on its mass. This is simple to understand that the ultimate source of energy of a star is its mass m. So if L is the luminosity of the star while it is on the main sequence, its lifetime on the main sequence TMS will be proportional to m by L. Since the mass luminosity relation is L is proportional to m to the power 3.5, for the main sequence stars of masses less than approximately 20 solar mass. For masses larger than 20 solar mass, the luminosity is probably directly proportional to the mass of the star, and we have TMS is proportional to m to the power minus 2.5, or TMS is proportional to 8 into 10 to the power 9 m to the power minus 2.5 years, where m is now expressed in the units of solar mass, and 8 into 10 to the power 9 year is the estimated main sequence lifetime of the Sun. So these are the figures showing the lifetimes and luminosities of the main sequence stars as a function of their solar masses. Connection between the turn-off and the age of a cluster. Let us now come back to the HR diagram of a star cluster. Remember first that in the plane of the HR diagram, the mass generally increases upwards. So in the terms of the main sequence, this means that the mass increases as we go to the blue color. So the turn-off points indicate essentially the masses of the stars which have started evolving away from the main sequence. If the turn-off point occurs in the region of blue color, it means that only the more massive stars of the clusters have evolved away from the main sequence. Since more massive stars have shorter lifespans on the main sequence, it means that the cluster is not very old. So on the other hand, if it in a cluster, the turn-off occurs in the region of red color, low mass stars as shown in this figure, it would mean that the cluster is very old, and since even the low mass stars have been able to complete their lifetime on the main sequence and have then headed towards the giant branch. Ages of open or galactic stars. So now if we arrange all the clusters in accordance with their turn-off points, we will arrange them in accordance with their ages as shown in this figure. So a composite diagram for open clusters in order of their turn-off. Remember, lower the turn-off, older is the cluster. The ages of open cluster range between a few million to a few billion years. The ages of globular clusters are much longer, between 12 to 14 billion years. The age of the oldest globular cluster conflicts with the age of the universe. So, attempts are continuously being made to define the ages of globular clusters to deal with the conflict. Blue stragglers. In the CM diagram of clusters, some stars are found on the main sequence above the turn-off point. So, being more massive than the stars at the turn-off, these stars should have evolved before the stars at turn-off. So, the existence of these blue stragglers has no simple explanation. It is believed that they were originally less massive but accreted mass from their binary companions and came to exist in their present location as shown in this figure. So students, this figure shows the typical CM diagram of an old cluster showing how a star might evolve away from the main sequence and then towards the main sequence. Hubble's law. Historically, ages of globular clusters became important when they conflicted with the age of the universe as estimated by the reciprocal of the Hubble's constant. As you might know, Hubble made a remarkable discovery in the earlier part of the 20th century that all the galaxies are moving away from each other. The speed of recession of a galaxy from us is being proportional to its distance, as shown in this figure. So this discovery came to be known as the Hubble's law and gave rise to the popular notion of expanding universe. It was argued that if the galaxies are moving away from each other at some time in the past, they must have been together at one point, from where an event popularly known as Big Bang sent them flying away from each other. So the age of the universe is reckoned from this event. It is estimated largely from the reciprocal of the slope of the Hubble's law. So initially, around 1930s, the value of Hubble's constant was estimated as approximately 500 kilometers per second MPC, which translated to the age of the universe of only 2 billion years. This was shorter than even the age of the Earth determined by radioactive dating of terrestrial rocks. With improvement in techniques, especially of distance determination, the value of Hubble's constant has been narrowed down to a modern consensus value of around 70 kilometers per second MPC. So this gives the age of the universe around 14 billion years, not very comfortably higher than the age of the oldest star clusters. So the notion that the age of the component of the universe cannot be longer than the age of the universe itself. It has prompted the astronomers to determine the age of the clusters as precisely as possible so that the conflict in ages can be resolved. So students, let us summarize what we have learnt in this module. Stars of a cluster can be assumed to have been born at the same time, so they have the same age. However, stars can differ in their masses. There can be small differences in the chemical compositions too. Stars of different masses have different lifetimes on the main sequence. After residing on the main sequence, the stars evolve away from the main sequence towards the giant branch. High mass stars evolve faster than the low mass stars. The turn-off point in the color magnitude diagram of a cluster gives the mass of the stars that have started evolving away. Since the time spent by these stars on the main sequence is known as the turn-off point, determines the age of the cluster. So there are few stars which are found on the main sequence above the turn-off point. These stars are called as the blue stragglers because they are not expected at that position. It is thought that these stars were initially less massive than the stars at the turn-off point, but accredited mass from their binary composition and found themselves above the turn-off point. The galactic clusters or the open are clusters, they are much younger than the globular clusters populating the central bulge of the galaxy. So their ages vary from a few million to a few billion years. The age of globular clusters are in the range of 12 to 14 billion years, accordingly uncomfortably close to the age of the universe itself. Efforts are being made to determine the age of the clusters more precisely to avoid the conflict with the age of the universe. Thank you.